Now to Chuck DeVal, the NASA Launch Manager.
Thank you, George, and good afternoon, everyone. It's certainly a pleasure representing Kennedy Space Center and the Launch Services Program for our first Atlas V. There's been a lot of hard work to get to this point. Our role in the Launch Services Program is for mission and launch management of the launch service. In addition, for this particular launch, because it was the first government usage, we also provided launch vehicle certification, which included over 120 people working on that endeavor. I'd like to thank JPL for the opportunity to be involved with MRO. I appreciate Lockheed Martin and ILS providing us with the launch vehicle and the launch service mechanism. I can tell you that all NASA reviews are complete to this point. We have one final range review this afternoon we'll get through. We do have inline work to go, and barring any bad weather, Clay, I think we'll be okay to get through with that. Just briefly going through the countdown, starting tomorrow evening. It's a long countdown. It starts about L-12 hours. The first major milestone we hit is the MLP roll out of the vertical integration facility. That will occur about 10:36 tomorrow evening. We have 2 built-in holds in the count for a total of 40 minutes. After we secure a few hours, we secure the vehicle at the pad. Perhaps we'll continue. We'll power on Atlas and Centaur, start doing some guidance checks, closed-loop flight termination systems, and start pressurizing the systems and chill down of Atlas storage tanks. We will have a weather brief at T-minus 2 hours and 10 minutes that prepares us for the cryogenic load. We have a built-in hold at T-minus 1 hour and 20 minutes. That's for 30 minutes. And then we'll go into our cryo load. We'll do the Centaur liquid oxygen first at T-minus 103 minutes. We'll do Atlas LOX at T-minus 90 minutes. And then we'll do Centaur hydrogen at T-minus 50 minutes. We'll do an open loop test with the range from the flight termination system at T-minus 40 minutes, about 7:04 a.m. We'll go into our second built-in hold at T-minus 4 minutes for 10 minutes. Coming out of that, the spacecraft will be going into on internal power at 8 minutes to launch. And we do our final launch pull at 7 minutes to launch. We'll have final flight pressurization, systems going internal, and arming the FTS system. The Russian RD-180 engine will light at 2.7 seconds, and we'll have liftoff at 7:54 a.m. on Wednesday morning. We do have an hour and 45-minute window if we need that, and we also have a backup day on the 11th for the range. I do have a brief video I would like to start that shows how we got to this point. There's the vertical integration facility, and what you'll see coming into view is the Common Core booster. This is built in Denver by Lockheed Martin, shipped by air to the Cape. It arrived on March 31st. This activity is shown on May 6th, it going into the vertical integration facility. The booster is 12.5 feet in diameter, about 106 feet long. There's a view of the Russian-built RD-180 engine and 2 nozzles, which it provides close to 900,000 pounds of thrust. It's fueled by liquid oxygen and kerosene, RP1. The booster holds 450,000 pounds of blocks and 169,000 pounds of kerosene. There's a good shot of that. Okay, the first stage up in the VIF. Next is the Centaur stage, the workhorse of upper stages. It arrived at the Cape on June 6th. It's also built up in Denver by Lockheed Martin. Doors of the VIF roll up, and this is on June 17th. Centaur is 10 feet in diameter. In this particular configuration, a single engine is 41 feet long. There's the vehicle designator, 007. It's powered by a single Pratt & Whitney RL-10 engine, which provides about 22,000 pounds of thrust. As opposed to the booster, this is a cryogenic engine, so it's using liquid oxygen and liquid hydrogen. There it is being set down in the inner stage to the Common Core booster. Okay, next up, the payload. The encapsulated payload, MRO, coming into view. Here it is arriving from the Payload Hazardous Servicing Facility, or the PHSF. This is the 4-meter version of Lockheed Martin's fairing. Spacecraft is about 14 meters from its solar array tip to tip, and 7 meters high. It weighs about 4,800 pounds. This was being conducted on July 28th, early morning of July 28th. Integrated testing followed, and now we're ready for rollout tomorrow evening. Turn it back to you, George.
All right, thank you, Chuck. And now for what the flight events look like, here is Mike Jensen, the Vice President and Chief Technical Officer for International Launch Services. Mike?
Thank you, George. International Launch Services and the Lockheed Martin Atlas program are very excited to have the opportunity to launch the Mars Reconnaissance Orbiter mission for our NASA customer. We recognize that MRO is an extremely important mission to NASA, and we also recognize that this is the first Atlas V launch vehicle launched for our NASA customer. There have been a total of 5 Atlas V flights to date, all of which have been on commercial flights, and all have been successful. In fact, the overall Atlas launch record is 76 consecutive successful launches since mid-1993. The MRO spacecraft will be launched on an Atlas V 401 configuration, and as Chuck said, is designated AVO 07. The 401 configuration is defined by a 4-meter diameter payload fairing, has no solid rocket boosters attached, and has a single-engine Centaur upper stage configuration. The vehicle is 188 feet tall and weighs nearly 740,000 pounds at liftoff with the MRO spacecraft. MRO will be the third flight of the Atlas V 401 configuration, and will also be the third and final Atlas launch this year. That doesn't mean that we're not going to be busy toward the end of the year. We are busy processing right after this launch for our next also important NASA launch, Pluto New Horizons, in January next year. The Atlas, the AVO 07 vehicle will inject the MRO spacecraft into a hyperbolic departure trajectory from Earth. The MRO mission will utilize a typical 2 Centaur burn parking orbit ascent profile, except the Centaur second burn will inject the MRO spacecraft into a hyperbolic orbit instead of an Earth orbit. There's a unique departure orbit for each day of the launch opportunity, which goes from August 10th to September 5th. As a result, the Atlas flight profile and the nominal sequence of events will vary depending on what the launch day is, as well as time into the launch window. For the planned MRO launch on August 10th, the launch window, as Chuck said, is from 7:54 to 9:39 Eastern Daylight Time, and has an hour and 45-minute window duration. To illustrate the Atlas V launch phase of the overall MRO mission, we will now show an animation of the Atlas flight profile and the nominal sequence of events to spacecraft separation. Again, this is for a launch on August 10th at 7:54. The AVO 07 MRO mission begins with the RD-180 ignition and liftoff from Launch Complex 41. The RD-180 engine is throttled to a sea level thrust of over 860,000 pounds. Shortly after liftoff, Atlas begins its initial pitchover maneuver to attain a flight azimuth of 104 degrees. At approximately 42 seconds into flight, it will begin its zero angle of attack phase of flight to minimize aerodynamic loads. At 85 seconds, the vehicle will experience maximum dynamic pressure. At 100 seconds into flight, RD-180 will throttle down to 95%. And then an acceleration of 5 Gs at approximately 3.5 minutes into flight, the RD-180 engine will throttle and maintain a constant vehicle acceleration. At 10.4 seconds before booster engine cutoff, the RD-180 will throttle down to 4.6 Gs and maintain that to BECO. After Atlas After the Atlas stage propellant depletion, booster engine cutoff, or BECO, is initiated at approximately 4 minutes into flight. 6 seconds after booster engine cutoff, the Atlas booster section is jettisoned, and Centaur first main engine start, or MES-1, takes place 16 seconds after booster engine cutoff, about 4 minutes and 19 seconds into the flight. 8 seconds after the Centaur main engine start, the payload fairing will be jettisoned. And Centaur and the MRO spacecraft are now on the first burn, the longer of the 2 Centaur firings. This 9.5 minute burn will inject the vehicle into a nearly circular parking orbit altitude of 100 nautical miles. Centaur first burn main engine cutoff, or MECO-1, will occur at 13 minutes 52 seconds into flight based on guidance commanded shutdown. This coast phase the Centaur and the MRO spacecraft will be in will vary from 27 to 40 minutes depending on the actual launch day and time. MES-2 will be initiated at guidance calculated start time at 49 minutes 52 seconds into flight and will burn for about 5.5 minutes. MECO-2 is also commanded based on guidance command, and then the Centaur will perform a maneuver to align to the separation attitude for spacecraft separation. Separation of the spacecraft will occur 2 minutes and 49 seconds after MECO-2 at approximately 58 minutes and 10 seconds after liftoff. Again, spacecraft separation will also vary depending on the actual launch day and window time. Go Atlas, go Centaur, go MRO. Back to you, George.
Thank you, Mike. And now to Jim Graff, the MRO project manager from JPL. Jim?
Thank you, George. First, for the complete Mars Reconnaissance Orbiter team, I want to say that we're all very excited about being here and being 2 days away from launch. It's extremely exciting. Many of us started working on this project back in the year 2000, so it's been a long 5 years worth of development. I thought what I'd start off with today is showing you some of the processing that we've done down at the Kennedy Space Center. So if we can roll the first tape, I would like to take you through some of the events that have transpired over the last 3 months. This is the spacecraft itself landing inside a C-17, and this happened on April 30th of this year. The spacecraft bus, there were many parts of the spacecraft. The bus itself was in the container that you're looking at right now, which is about 10-foot cube. The container was taken out of the C-17 and brought into the payload hazardous servicing facility here at the Kennedy Space Center, and then was inspected, as you can see right here. After that, we went through a number of tests on the spacecraft, but before we could actually start working on it physically, we had to put it into the rotation fixture, which is you're seeing right now. The rotation fixture allows us to move the spacecraft into different orientations so we can get easy access to it. Here we're putting on the 10-foot diameter high-gain antenna onto the spacecraft itself while it's in a horizontal position. The next thing you're going to see is the firing of separation nuts that are retaining the solar array during the launch phase. After that, we go ahead and actually try a deployment. We successfully deployed the solar array. Now, of course, the solar array deployment happens in 0G, and we're in 1G, so we had balloons that were added to offset the sag due to gravity. And here you can see one of the 2 solar array wings that we have. And now you're looking at the entire spacecraft fully assembled. We moved it to another stand, which is what you're going to see right here, which is the final stand for doing all the functional tests, the verification tests on it. This is a very hazardous procedure, as you can imagine, taking a fully assembled spacecraft and moving it from one facility to another. After we finish with that set of testing, we moved it to a third facility, a table. This is a spin table, and we actually spun the spacecraft up to 5 RPM. We did this not because of the launch phase. The Centaur does a great job in maintaining our orientation in a 3-axis stabilized condition. But during Mars orbit insertion, we want the spacecraft center of mass to be aligned with the thrust vector. So we went and we ballasted it with some additional mass. Then we came along and we encapsulated it in the fairing, the payload fairing, and this is what you saw earlier. I believe it was in Mike's talk. and transported out to the launch vehicle. That happened on the 28th of July, so the whole process that you have seen is 3 months condensed just into just a few minutes. Let's go to the first view graph and talk about the spacecraft itself. The spacecraft is a very, very large spacecraft. It weighs over 2 tons. Half of that is dry mass, we call it, and half of that is fuel. The solar arrays produce about 6 kilowatts of power at the beginning of life here at Earth. When we get to Mars, and we're the furthest distance from the Sun, they produce about 2 kilowatts of power. In addition, you'll be looking and you can see that we have a very large solar array which is 10 feet in diameter. The physical dimensions of the spacecraft is that they're about 44 feet from tip to tip, from solar array tip to solar array tip, and about 22 feet high from the bottom of the Mars orbit insertion thrusters all the way up to the top of the high gain antenna. Next view graph, please. How does this spacecraft compare to ones that we have presently in orbit? You can see the comparison to the Mars Global Surveyor and to Odyssey. You can see physically it's much larger. We have many more instruments on board, and the instruments themselves represent a much more capable payload suite than we've been able to fly to the red planet before. A couple of things to keep in mind as you look at the high gain antenna comparison between the spacecraft. The Odyssey and MGS are flying a 1 meter diameter antenna. We're flying a 3 meter, actually it's almost a 10-foot diameter antenna for the Mars Reconnaissance Orbiter. Why are we doing that? We're doing that because the data volume is key. If you want to start an intensive investigation of the planet itself, you have to start increasing your ability to cover vast portions of the surface. You need to increase that coverage, and you need to do it at a much higher resolution. When you couple those two things together, that translates into more and more data. So what we have done is taken a major step forward in the capability of this spacecraft to return data. Essentially, the two spacecraft you're seeing here that are returning great data, MGS and Odyssey, are in a kilobit per second range. They're bringing their data back, we think of it as through a straw. And when MRO is there, we're going to start opening up the fire hose and bring it back at 5.6 megabits per second. Next view graph, please. What does that translate into? That translates into a lot more data. You can see here that we can get upwards of 34 terabits of data being brought back in our 2 years of science operation. When you add up the missions that you see here and you multiply by 3 to 4 times, you're starting to get up to the capability of MRO to provide data back from Mars back to Earth. So we are going to be awash in data which will enable us to better understand the planet as a whole. Next view graph. We're not only sending 6 science instruments and have 2 science investigations that actually use the engineering subsystems on board the spacecraft, we are also flying 3 additional engineering payload units. The first one I'm going to talk about is the UHF radio. We call it Electra. And this is the device by which we communicate to the landed assets, to the rovers on the surface. Right now, this is a technique that's being used presently. The rovers that are down on the surface are communicating through Odyssey, and they're bringing back about 95% of the data returned comes through this relay. And that's because it's a lot more efficient to send a lot of data a very short distance up from the surface to one of our orbiters than it is to send it all the way back to Earth. So that's the first unit I'm going to talk to. The second one I'm going to talk about is the Ka band. We are, in fact, pioneering the use of Ka band for science. Ka band is a different frequency, and we can return 4 times the amount of data for the same amount of energy that we're putting into Ka band over what our traditional frequency is. So that we're taking a major step forward with the Ka band experiment. Lastly, I'm going to talk about the optical navigation camera. This is used only on approach, and it looks at the moons of Mars against the backdrop of stars. And that enables us to more accurately determine our position relative to Mars itself. This is not a device that we are using at all for MRO. This is a device that is what we call feed forward. This is a technology that we are pioneering for the use of the Mars Science Laboratory so that they can more accurately enter into the Martian atmosphere. The error, when coupled from the OpNav camera to the radiometrics that we normally get, can be reduced into half of what we normally would have. So that will enable us to enter the atmosphere with the landers more accurately and be able to have more pinpoint landing. So those are the three engineering payloads that we're flying. And what I'd like to do now is show you an animation and take off from where Mike left off, and that is we will see the booster fall away here, and we'll go through and jettison the fairing, and we're on the Centaur. What we do then is we actually separate about 58 minutes after launch, and then the spacecraft is on its own. The first thing it will do is to deploy the solar arrays, and that'll be in a 4-part process. And then we also deploy the high-gain antenna, and you can see that here in the animation. We are transmitting at that particular point to a station in Japan, which is picking up our data and relaying it back to JPL and to Denver. It takes us about 7 months to go from Earth to Mars. And we actually wind up being ahead of Mars during that phase, and Mars catches up to us and pulls us down into their gravitational well. In March of 2006, we actually approached the planet over the south pole of the planet, firing our Mars orbit insertion thrusters. We fire them for about 30 minutes. Half of that is seen by Earth. The other half is behind the planet, and we will not know. It'll be white knuckle time during that process. Once we get captured into orbit, it's a very elliptical orbit. It's very close to the planet. It's about 100 miles on one side, and it's about 20,000 miles on the other. And we have to bring the orbit down, and it takes about 6 to 7 months in a technique called aerobraking to reduce the orbit from that very elliptical one down to our final science orbit, which is roughly a 200-mile orbit. And once we achieve that, we will be in a science orbit for 4 years. 2 years of that will be to acquire science from the instruments, and 2 years will be supporting a relay phase where we're actually talking to assets on the surface. And that is the mission in a nutshell, and I will say this, that from the whole Mars Reconnaissance Orbiter team, we really appreciate the support we've had down here at the Kennedy Space Center. With that, George.
All right, thank you, Jim. We'll look now at the weather for Wednesday morning. Clay Flynn, the Atlas V launch weather officer. Clay?
Good afternoon. Conditions are favorable for the launch both Wednesday and Thursday. The subtropical ridge axis should be to our south through the middle of the week. With that, that should give us southwesterly flow. And southwesterly flow pattern is a favorable pattern for an early morning launch, not so necessarily for an afternoon launch, but for the morning launch it's a good flow pattern. So the conditions that we look at launch time are just scattered low clouds, scattered at about 2,500 feet, scattered at 25,000 feet. Unrestricted visibility. Wind should be from the southwest and relatively light in the 8 to 12 knot range. We will have expect to have some isolated showers off the coast, and that would be our principal concern for launch, going with about a 20% chance of violating launch constraints. And that would be associated with thick clouds associated with those showers, as well as cumulus clouds associated with those showers. But both Wednesday and Thursday look pretty good. 20% forecast looks similar both days. George?
Thank you, Clay. And we're ready now to take questions. Please give your name and affiliation when the microphone comes to you. And we'll start here in the front with Justin.
This is Justin Ray with spaceflightnow.com. I guess for Chuck, could you talk about the range situation? If you didn't go on your first 2 attempts for whatever reason, would you have to stand down for the GOES launch, or would they be willing to move out and let you guys have a few more tries?
Well, I guess the answer to that is it depends. We've got the 10th and the 11th. GOES is conditional on the 12th, and as you probably know, their eclipse window only allows them to launch through the 14th. So if we didn't make the 10th or the 11th, we'd have to, obviously, it would depend on why we didn't make them, and then it would be an agency decision as to who gets priority.
And the second question for Jim, could you talk a little bit about, after separation, a little more detail on when the arrays actually deploy? Will you be seeing that in real time? When will you be able to confirm spacecraft health?
We go ahead and deploy. The first thing we do is a rate damping. That takes a minute or so. And we will turn on, at that particular point in time, the transmitter, even though we haven't deployed the high gain. So we will start transmitting, and at that particular juncture, within 2 minutes of separation, the Japanese station could be picking us up and sending the signal back to JPL and back here to the Kennedy Space Center. Right after that, we will deploy the solar arrays. That takes about 15-20 minutes to deploy the solar array, and then the high gain follows that. All of the deployments are completed within 38 minutes after separation. We acquire Goldstone at about 20, I think it's about 25 minutes right at the start of the window after separation. So we could see the final end of the deployments actually from Goldstone, although the Japanese station has great coverage for us during that entire phase.
What is the Japanese station that you're using?
It's not a NASA asset, no. It's from JAXA.
Craig?
Craig Cavalt with Aviation Week. Kind of following on the same topic, Jim, discuss the momentum wheel spin up and timing.
Well, what will happen is, first of all, we will, the Centaur will put us in a slight spin before they release us. We'll actually have a 0.3 of a degree per second spin. After that, we will go into safe hold mode, which is scheduled. That's part of our basic plan, is to take the spacecraft down to the most fundamental level that it can go. Then we will go ahead and we will be on thrusters at that particular point in time. We will not be on reaction wheels. And we will go through the deployments with the thrusters. We won't start the reaction wheels until later.
But the wheels start how much later post-SEP?
I'll have to get that answer for you, Craig. I don't really know right now.
Is it just minutes, or do you take a whole day to?
Oh, no. It's within minutes.
Yeah, that's fair enough. On your first TCM, do you use all 6 main engines?
Yes, our first TCM is designed to actually use the Mars Orbit Insertion engines, the MRO, the MOI engines, and it's about 4 meters per second is the burn. We will use all 4 of them, and we did that deliberately so we could calibrate the thrusters early in the mission so we're ready for MOI when it comes about.
And one last for Mike on the Atlas. Can you just discuss your inclination? I realize it's a little different depending on what day, but for August 10th, 11th, what is it?
It's about 39-degree inclination. And again, that's associated with the flight azimuth of 104 degrees. And as I said, we do switch parking orbit, and the inclination is the variable when we do that. And there will be an associated flight azimuth shift as well later in the launch opportunity. The time at which we switch parking orbit is the 19th, so we'll be on the same parking orbit and flight azimuth up to through the 18th.
Chris?
Chris Kreidler from Florida Today for Jim. First, is 4 years considered a minimum lifespan for the spacecraft?
The answer is no, Chris. Actually, the full lifetime of the primary mission is 5.5 years. We spend about roughly 1.5 years getting into our final science orbit between the cruise phase and the aerobraking phase. Then we spend 2 years acquiring science and 2 years doing relay. We end the primary mission right now, December 31st, 2010. We have sufficient fuel on board to actually operate until 2014 in our primary science mission, so we can extend the life of the spacecraft for some time.
And why wasn't Ka-band used before? What challenges were involved?
Oh, good question. Actually, there have been some experiments for Ka-band previously on other spacecraft from deep space, but there hasn't been any real application of it to the science return. And the reason for that is because when Ka-band passes through our atmosphere, water vapor can attenuate it. So if you have rain over the station, it can have an impact on your ability to acquire the data. we have been using, and even on this mission we will use X-band, which does not have that attenuation once it comes through the atmosphere. So we have put in place with the Deep Space Network some mitigation measures which we will be trying out. And that includes a retransmission request where we acknowledge that we did not get all the data, and this is out at the station itself, and we send a request back up to the spacecraft immediately saying retransmit or save this data and retransmit it at another time. So we're putting that capability in place.
All right, we have a question down here on this end.
Leo Enright from Irish Television. I just wanted to understand a little bit about this TCM maneuver. As I understood, it's being driven primarily by planetary protection issues. Is there anything unusual about what seems to me to be a fairly complex series of maneuvers? You know, you have to do certain things to get to Mars as a result, it seems, of the targeting of the booster. Were there trade-offs discussed, or is this absolutely bog standard?
I assume, Leland, that's for me? The answer is yes. We did a lot of trade-offs on this. There are a couple of things. First of all, you're going to bias your trajectory to be slightly away from the planet, and that is for the planetary protection aspects of the mission. We don't want to have a spacecraft potentially that would have a problem that would crash into the planet. So we have to do a maneuver. We knew that. Then the question was the size of the maneuver, and we debated whether it should be let's say 1 meter per second, 4 meters per second, or even more. We decided on the 4 meters per second because we wanted to be able to test out the main engines. And that was about the minimum we thought we could do and test those main engines. So we're really addressing two issues. One is the planetary protection, and two is getting a good trial run on those main engines before we actually have to use them for the Mars orbit insertion.
Any further questions? It's right here, the red shirt.
Hi, Curtis Kruger with St. Petersburg Times for Mr. McQuiston. I wondered if you could just talk in general terms about what are the most important science objectives of this mission in terms of the water and future manned and unmanned missions.
Well, I hate to put you off, but there's an entire science panel that's going to give you that in detail. A quick overview. Obviously, we've learned a lot about the history and the role of water in the history of the planet with the rovers and with Odyssey and with Mars Express. This will not only help us continue that understanding with mineral composition geology, but one of the most capable atmospheric missions that we've had as well. Put those together and also look for interesting sites to help us continue our strategy and follow the water for Phoenix and for Mars Science Laboratory. It's critical with the high-res imager as well as the context camera. Helps us with identifying those sites as well.
Craig, a follow-up?
One last quick one on TCM. About how many minutes duration is TCM and approximately? And on attitude control, are you banging away there with all 6, I guess, thrusters to hold attitude?
Yes. I'll check this, Craig, but I believe that we fire the thrusters for about 8 seconds, and that's about it. We fire all 6 at the same time, and we use a middle-size thrusters, which are meant to control the attitude of the spacecraft while the main engines are firing. We call them TCM thrusters. So we actually have 3 levels of thrusters on board. We have the small ones, which provide attitude control. We have the TCM thrusters, and then we have the main engines.
All right, at this point, we're going to transition directly over to our mission science briefing, just long enough to change our panelists on the dais, and we'll be back. And one programming note that we will replay both of these briefings on NASA TV today at 3 o'clock and 5 o'clock. So in just a moment, we'll be right back. Thank you.